So as I mentioned a little while ago, today we are going to cover mesh analysis. Okay. So mesh analysis is another tool or system for writing a system of equations that will allow us to solve circuits. We're going to be writing multiple Kirchhoff's voltage law equations as opposed to the multiple Kirchhoff's current law equations we wrote with nodal analysis. Students tend to prefer mesh to nodal just because you don't have a bunch of fractions and all of that kind of stuff. That's really the only reason I can think of. They're both equally powerful, but mesh can only be applied if we have what's called a planar circuit. So what I mean by that is we have to be able to literally flatten our circuit out into a single plane. So we couldn't do mesh analysis on a cube of resistors or something like that. Not something that you're going to see very often. Most circuit boards and things like that are a flat plane with circuits connected. But there is that caveat that mesh can only be applied to planar circuits where nodal can be applied to anything. Okay. All right. So we are going to learn the mesh analysis technique by analyzing a circuit, much like we did learning nodal on Wednesday. So I'm going to start with the following circuit. We'll have a 10-volt source here. A 9-ohm resistance here. 2 ohms here. 4 ohms here. 5-ohm resistance down here. Branching off from this point, we have a 1-ohm resistor, a 7-ohm resistor, a 3-ohm resistor, an 8-ohm resistor, and I'm actually going to make a change here. A 5 IX voltage source, and let's consider IX to be the current flowing down through this 2-ohm resistor. So our first step in mesh analysis will be to identify our meshes. So who can remember what a mesh was from the first day of class? So a mesh isn't any closed loop. It's any closed loop that doesn't contain a smaller closed loop. So this circuit contains exactly 3 meshes, right? So we're going to have this mesh. We will have this mesh, and of note here is that I am very much indicating a direction. We'll talk about that in a moment. And this mesh. Today is pretty much the only day you're going to see me identify my meshes like this because I want to make it very, very obvious the path that we are taking. Usually I use a shorthand that would look something like this. Just a simple loop in the middle of the mesh that lets me know what direction I'm following things around. But today, to be blatantly obvious about the paths that we're taking when we're writing these KVL equations, I'm going to use the larger one. Okay. Our second step oh, good God, will be to label our mesh currents. Okay. So I'm going to call this current IA. This mesh will carry a current IB. And this mesh will carry a current IC. So the way that I have identified and labeled my meshes here means that I am making an assumption that these mesh currents are flowing clockwise around their individual meshes, right? So my mesh current IA represents the current flowing through the 9 ohm resistor from left to right, or the current flowing through the 5 ohm resistor from right to left on the bottom. My mesh current IB represents the current flowing through the 1 ohm resistor in series with the 7 ohm resistor. Similarly, my mesh current IC represents the current flowing down through the 8 ohm resistor. So we can relate these mesh currents to traditional currents like we've been dealing with in previous classes easily. So just to make this real obvious, this current is also the exact same thing as mesh current IA. This current is the exact same thing as mesh current IB. And this current is the exact same thing as mesh current IC. Now, where things get a little bit tricky is when we have an element that is shared between multiple meshes, okay? So we're going to talk about that right now when we get into step number 3, which is going to be express our controlling variables in terms of our mesh currents. So our controlling variable in this case is the current IX that's flowing down through our 2 ohm resistor there in the top middle of the circuit. And so how we're going to write this expression is we're going to figure out what the total current flowing through the 2 ohm resistor is. So the 2 ohm resistor is between mesh A and mesh B. So we should expect a contribution from mesh current A and mesh current B. If it were between meshes B and C, we'd have a contribution from B and a contribution from C, and so forth, right? So what we're going to do is we're going to say that the mesh current that's flowing in the same direction as IX will get a positive sign, and the mesh current that's flowing in the opposite direction as IX will get a negative sign. So which one's flowing in the same direction, A or B? A. Right, so as A flows around its clockwise path, when it's going through the 2 ohm resistor, it's flowing down, which is in the same direction that is indicated for IX, right? So IA will get the positive sign. When we follow mesh current B around its clockwise path, it's flowing up through the 2 ohm resistor, which is in the opposite direction as IX is defined as. So that's why it gets the negative sign. So much like what we were doing with voltage relationship equations for nodal analysis, positive polarity terminal minus negative polarity terminal, here we have same direction minus opposite direction. So it's a similar concept. We're just dealing with currents now. So this is our controlling variable relationship here. We'll use this style of relationship once we start adding current sources into our circuits here in just a little bit. Because we only have voltage sources in this circuit, we're not going to have to worry about super meshes or anything like that just yet. So instead, we can go ahead and start writing our Kirchhoff's voltage law equations, right? So step 4 will be to write a KVL equation for each mesh. So we have 3 meshes. So I'm going to have a KVL at mesh A, KVL at mesh B, and a KVL at mesh C. And I'm going to write these KVL equations just like I would write any other KVL equation. I'm going to start at the bottom left-hand corner and just follow my current around its path. Right? So if we start with mesh A, and I'm starting at the bottom left-hand corner, the first thing I see is the negative polarity terminal of the 10-volt source. So I'm going to have negative 10 volts. The next thing that I see is a 9 ohm resistor. And so I'm going to use Ohm's law to write the voltage drop across that 9 ohm resistor as simply 9 ohms times IA. Okay. So when we're writing our KVL equations, we are going to assume that the current that we are following is flowing into the positive polarity terminal of any resistor that we see. So that's going to mean that all of our IA terms in this first equation should have a positive sign. And when we're writing a KVL equation for any other mesh, all of our IA terms are going to wind up having a negative sign because we're following a current flowing in the opposite direction. Now we see our 2 ohm resistor. And it's carrying a total current of IA minus IB. Then we have our 4 ohm resistor, which is carrying a total current of IA minus IC. And then we have our 5 ohm resistor carrying a total current of IA. So whenever our elements are on the outside edge of a circuit, they're only going to have one current flowing through them. Whenever they're on the interior of the circuit, they're going to have 2. Those are all 1, 2, 3, 4, 5 different components. So 5 different voltage drops set it equal to 0. And now we're ready for our KVL at mesh B. So I'm going to let you guys take a crack at what's going on for mesh B. Let's start here. So do you guys want to call stuff out, or do you want me to call on individual people? We're starting at this node. So when we are writing our equations for IB, we're following IB around. So the assumption is that IB is flowing into the positive polarity terminal now. When we write our KVL equation for mesh C, we're going to assume that IC is flowing into the positive polarity terminal. So that whatever mesh we're working on, the corresponding current gets positive signs and any opposite current gets negative signs. So IX isn't a mesh current, so I would argue that it shouldn't show up here. IA, exactly right. IB minus IA. What's the next thing we have? 1 ohms times IB, all right. And then 7 ohms times IB, and obviously we could have done a resistor combination here and just called it a single 8 ohm resistor times IB, and we'd wind up getting the same result. What's the next thing that we see? IB minus IC. Great. Thank you guys for being so responsive today. I hear lots of people chiming in. That's wonderful. Those are the only 4 elements that are in mesh B. So we have all of those voltage drops taken care of. Now we're going to write KVL at mesh C. So starting from this bottom node here. Absolutely right. Okay. So I would literally just write this as minus 5ix, right? We can worry about substitutions later on, but whenever I see a voltage source, I personally, if I see the negative polarity first, I just do negative and then whatever the voltage source tells me. You're 100% right that we're going to wind up substituting in the relationship that Ix is equal to Ia minus Ib. Or at least those of you with a calculator that can only do 3 equations, 3 unknowns will likely use that substitution. Minus 5ix is equal to 0. Right now we have 4 equations and 4 unknowns. So we're going to be at step 5, which is to solve this thing. Solving this system of equations is no different than solving the system of equations using nodal analysis. So instead of using a calculator here, I just want to show you guys how to use MathCAD to solve systems of equations. Solve. Erase this. So you're gonna have to bear with me as there's gonna be a lot of switching back and forth between the screens so that I can remember the equations and all that kind of good stuff. One thing that I do want to point out here is that there's currently an issue with the VPN on campus, which means that it's difficult, not impossible, but difficult to access MathCAD from off campus. If you need MathCAD access off campus to do your homeworks until this issue gets resolved, you need to go down the hall and speak with Miss Ashley Osborne in the project-based learning office. She will set you up with an Amazon Workspace account that will allow you to access MathCAD from off campus. Or you could just do your homework while you're on campus and then you're good to go. So anyway, in order to solve a system of equations, we are going to use a solve block, which is found up here. It's under the math tab and it is the second option. Okay. So this solve block has 3 different sections. We have guess values, constraints, and solver. And so guess values is effectively where we declare our variables that are going to be solved for. Okay. So I'm going to have 4 guess variables, IA, IB, IC, and IX. So oops, I have caps lock on. I'm going to use subscripts. You don't have to. To get a subscript, it's control minus. So that's IA. And then I'm going to hit shift colon. And I'm just going to arbitrarily guess 1 amp for the value of this current. For the most part, the guess values that you choose will not matter. Every now and then, actually, let me rephrase that statement. For a system of equations like this, where we have simple linear relationships, for the most part, your guess values will not matter. Okay. Every now and then, you will try to solve a system of equations and it will tell you that no solution is found. Change a couple of guess values and it'll usually be able to find a solution. For a circuit like this, there's always only exactly 1 solution because we have a linear system of equations, right? Now, that being said, if you tried to use a solve block like this to solve polynomial equations and things like that, which it's perfectly capable of doing, the answer that it gives you back is going to be the one that is closest to the guess value you put in. So you should expect for a cubic equation, there would be 3 answers. This is only going to return 1 of them, and which answer it returns depends on what you put in as your guess value. So you'll have to play around with the guess values in order to get all 3 results and all that kind of stuff. So I just want to make you aware of that. So I'm going to go ahead and declare a variable IB for 1 amp, a variable for IC having a value of 1 amp, and IX having a value of 1 amp. So these are the 4 different quantities that I am going to solve for. Now, below this, I'm going to start writing in my equations. So these are going to be the constraint equations. And as soon as I type in an actual equation, it's going to expand this bracket to cover it. So you don't have to worry about where you're putting things in here, really. It should just be guess values on top, constraints, and then solver at the bottom. And it'll make the brackets fit everything as it goes through. Okay. So our first equation that we wrote was Ix is equal to Ia minus Ib. So I'm literally just going to put that in. Ix, I'm going to do control equals Ia minus Ib. So notice that we're using a different equal sign here. This is the control equal, and what it means is what is on the left-hand side of the equal sign must absolutely be equal to whatever is on the right-hand side of the equal sign. Okay. We're going to write similar equations for the next thing. So we're going to have negative 10 volts plus 9. So let me talk to you about how I put units in here. If I get this Zoom thing out of the way, we have a drop-down menu for symbols here. There are lowercase Greek symbols and uppercase Greek symbols. So that's one way to do it, not the way that I'm going to do it. We can also literally just go into the units tab and find resistance, kilo ohms, mega ohms, and ohms. Also not the way that I'm going to do it. The way that I'm going to do it is I'm going to give myself an uppercase W, which probably seems really weird, and then control G turns it into a Greek character. And since lowercase w looks like lowercase omega, MathCAD assumes that uppercase W is for uppercase omega. So that's how we can do the ohm symbol without having to go into any of those dumb drop-down menus, which annoy the hell out of me. Okay. So 9 ohms times IA. Then we have 2 ohms times Ia minus Ib. Then we had, I think it was 4 ohms times Ia minus Ic. I made a mistake there. Plus 5 ohms. What the heck happened to the rest of my equations? Let's see. Yeah, so 4 ohms Ia minus Ic, 5 ohms times Ia. Oops. Control equals to 0. So one thing that I do want to point out here, I am in the habit of using units for literally everything because I firmly believe that it is good practice. You don't have to use units for MathCAD. It'll just spit out a number if you want it to or whatever. But if you're going to use MathCAD for working homework in this class where it's looking for specific units at the end and all that kind of stuff, I believe that using units the whole way through can be of use. You do have to use units for literally, it's either everything or absolutely nothing. You cannot play fast and loose with the units. It will tell you the units aren't compatible and won't actually solve the system of equations if you don't use units throughout. So just wanted to let you know that. Let's look at our next equation here. So 2 ohms IB, yes.
Does it matter if MathCAD guess value solve block are meshing together?
So not right now. So if you notice the bracket here, it's literally just the text that's overlaying. But the little bracket here is just guess values is up here and constraints are down here. Now, if you find that the brackets start overlapping each other, what that typically means is that you've accidentally used the wrong type of equal sign in your constraint equation. So if I, for instance, did, of course, it's not going to work. now that I want it to work. I'm trying to make a mistake intentionally and it's telling me that I can't do it. But I should be able to put a shift colon equal sign here, and it would cause the guess value thing to extend into where I'm writing my constraint equations. And that lets me know I've made a mistake by putting the wrong type of equal sign in. Or at least it used to let me do that when I was using MathCAD 5 and 6. Maybe 8 just won't let me anymore, which would be great, but yeah. All right, so 2 ohms times IB minus IA. Plus 1 ohm times IB. Plus 7 ohms times still IB. Plus, I forgot what's next. 3 ohms IB minus IC. Hitting shift too early. 3 ohms times IB minus IC. Control equals to 0. And then we have our fourth equation. 4 ohms IC minus IB. Plus 3 ohms IC minus IB plus, I think it was an 8 ohm resistor times IB or IC, yes. Yes, you're right. Thank you. That's what happens when I'm trying to do this stuff from memory. Absolutely right. Thank you. This is just times IC. And then we have minus 5 IX. So here's where we're going to have a little bit of trouble. Okay, so I'm just going to put in 5 IX here equal to 0. And I'm fully expecting this to give me an error once I try to solve it. Here's something, another thing that isn't required, but something that I have got into the habit of doing is I store the results of my solve block into a matrix. So the reason why I do this is because everything that's inside the solve block only exists inside the solve block unless I tell it to store it elsewhere. So if we were trying to calculate a power or something like that, we would have to manipulate the values from our solve block outside of the solve block in order to calculate a power. And so I have just gotten into the habit of storing things in this matrix. So I'm going to have a matrix of IA, IB, IC, and IX. I'm going to shift colon find IA, IB, IC, and IX. And I'll press equal here, and I get an error. It says the units are not compatible because I didn't put units on that 5 that's multiplied by IX. So effectively it's saying I have a voltage 4 ohms times IC minus IA plus a voltage 3 ohms times IC minus IB plus a voltage 8 ohms times IC minus a current 5 IX. So I need to explicitly state that that 5 has units of volts per amp. And now I get results. So this is what I was talking about. You either need to use units for everything or use units for nothing, right? Because we didn't put a unit on that one single thing here, we weren't able to get an answer. But as soon as we put the correct unit on it, it spits out results. Okay. So IX 0.417 amps. And now let's talk about what I was just mentioning a moment ago. I'm going to switch back to the other screen so we can define a power or something, and I'll show you how to use MathCAD for that. I'm sorry, what was that? Yes. Let me see what you have. Oh, that's a normal equal sign. All right, so let's look back over here. Let's say that we want to find the power supplied by our dependent source. That's going to be something pretty straightforward, right? We need the voltage drop across our dependent source, which is simply 5Ix times the current flowing into the negative polarity terminal of our dependent voltage source, which is just IC, right? So we come into MathCAD here. If I can find my cursor. We could say that P dependent is simply 5 volts per amp times IX times IC, and we get a power measured in watts, right? Let's see what would happen if I didn't put that matrix on the left, if I didn't store these variables. It doesn't know what anything is, because everything that's in the solve block is only in the solve block. That's why I use that matrix. We can't do math with anything that's inside the solve block or any of those results of that solve block unless we store them in that matrix to be used outside. So even if I know that I'm not going to have to use them later, I still store everything in a matrix just for the sake of argument. It's just, in my opinion, good practice. And then it's fixed. All right, so we have developed a method for solving circuits that contain voltage sources using mesh analysis. Now let's break things and throw current sources in, just like we did with nodal analysis with voltage sources. Okay. So I'm give you guys another circuit to look at. So here's the circuit. I guess I should probably tell you what this dependent source is and also define my current IX. like so. So when we're doing nodal analysis, we had to write voltage relationship equations. When we're doing mesh analysis, we had to write voltage. Let me start over. When we were doing nodal analysis, anytime we had a voltage source, we needed a voltage relationship equation. When we are doing mesh analysis, anytime we have a current source, we are going to need a current relationship equation. Okay. So our first few steps are going to be exactly the same. Identify our meshes. And label our meshes. So this guy right here will be mesh current IA. Here's B. Here's C. Here's D. So we've identified our meshes, we've labeled our meshes. Now we're going to be at step 3. Write our controlling variable equations. Or express controlling variable in terms of mesh currents, I think is how I said it earlier. So in this case, we have another current, IX. What's it going to be in terms of our mesh current? ID minus IC. Because we have current sources, we're going to need to write current relationship equations for all current sources. So we have 2 current sources here. We have a 5 amp current source. And we're going to write this current relationship equation exactly like we wrote that equation for IX just a moment ago. We can see that IC will be in the same direction as the 5 amp source. So IC is going to get the positive sign. IA is in the opposite direction, so it gets the negative sign. So anytime we have an interior current source, so a current source that's in the center of the circuit, really just not on the periphery of the circuit, we're going to express it as a difference in currents. And then we'll see for our 6 amp source, because it's on the edge, it's only going to be related to a single mesh current, just ID in this case. Two. Let me write that 2 better so that it's more clear. Thank you, Ian. Is that clearer? Okay. Okay, so we're at step 5 now. Much like we had with our supernodes, we're going to run into a problem if we simply try to write a KVL equation here. So let me explain what's going on. So if we write KVL at mesh A, we are going to have, let's see, 10 ohms times IA. Plus 4 ohms times IA minus ID plus 2 ohms times IA minus IC plus the voltage drop across the 5 amp source. There's no way for us to express the voltage drop across the 5 amp source in terms of our mesh currents. Okay, so we have a little bit of a problem here. So what we're going to do is we are going to create a super mesh, okay? And so a super mesh is what we're going to use to avoid expressing the voltage drop over a current source, particularly over an interior current source. Our super mesh is just going to be the smallest possible combination of meshes that avoids that current. So I'm going to scratch this stuff out here. We hit a problem, so we're not going to be able to use it. What we're going to do instead is we're going to take this path that I'm going to write in gray. Sorry about that. So this path that I've written here in gray combines meshes A and meshes C, or mesh A and mesh C, right? If we follow this path, we won't wind up taking the voltage drop over that current source, okay? Because this super mesh contains two meshes, we need to be able to get two equations out of it. One of them is going to be this KVL equation around this super mesh path. The other one is just that current relationship. We already have one of the two equations that we need to get out of those two meshes, okay? So we're going to write our KVL equation. Around any super meshes. So in this case, that's going to be KVL at super mesh AC. 10 ohms times IA. Four ohms, IA minus ID. Now we're going down through the 5 ohm resistor. So that's 5 ohms IC minus ID. All right. So just to be clear here, as soon as we leave where mesh A is, we should no longer see IA in any of our equations, right? Now we're going down through the 5 ohm resistor. The 5 ohm resistor sees a current IC flowing down, a current ID flowing up. So that's why we have 5 ohms times IC minus ID. Coming along the bottom, we then see the negative polarity terminal of our 2ix voltage source. So that's going to look like minus 2ix. Then we see the 3 ohm resistor. We're back to following IA. Set that equal to 0. So I just want to look here at how many equations that we have. So we have one equation, two equations, three equations, four equations. And by my count, we should wind up having 5 total equations because we have 4 meshes and then that quantity IX, right? So our next step is going to be to write KVL equations at any remaining meshes or around any remaining meshes. Which for our case will simply be mesh B. For mesh B, we have negative 4 volts plus 3 ohms times I B minus IA plus 2IX is equal to 0. And here we have equation number 5.
Isn't that we're doing one just for B, because B and the other equation?
So that's a fantastic question, right? Why? Let me rephrase your question slightly. Why aren't we writing a KVL equation around mesh D? We can't write a KVL equation around mesh D. Because it contains a current source along the perimeter, there is literally no combination of meshes or anything that we could do to avoid taking that voltage drop. So anytime we have a current source on the edge of a circuit, we are only going to have a current relationship for that mesh, which is what was just said a moment ago. We've effectively already defined it, so we don't need any more information about that particular mesh anyway, right? Ian. So I guess you could think about it that way. That's not particularly how I think about it. Like I said here, if there's literally no Kirchhoff's voltage law path that we could take that includes mesh D as a whole here, that is able to avoid taking that voltage drop over the 6 amp current source. We can't write the voltage drop across the 6 amp current source in terms of our mesh current. So much like when we were dealing with super nodes that contain the ground or the reference node, we don't write KCL equations there. If we have a mesh that contains a current source on the perimeter, on the outside edge, we don't write a KVL equation for it.
That's kind of the reason why we need the super layers for the bottom.
Right, because we have to avoid the 5 ohm resistor. Another question that you guys very often ask me is, what about that 2 ohm resistor? Smack in the middle, and then a single equation. Does not matter. Right. Effectively, when we add those two meshes together, right? If we wrote a KVL equation around mesh A, where we were following mesh current IA, we would have 2 ohms times IA minus IB. When we wrote a mesh current or a KVL equation around mesh C, we would have 2 ohms times IC minus IA. And when we add those two mesh equations together, those voltage drops cancel each other out because they're of equal magnitude but opposite polarities. So we just skipped proving that because I didn't feel I needed to, since we did the same thing in our nodal analysis. So at this point, it's simply solving this system of equations, which you could do by a couple of substitutions here. We'll break this down into a 3 equation, 3 unknown system if you wanted to do it by calculator. Or you could use MathCAD or whatever the heck you felt like, even Excel apparently. So I'm not going to bother actually solving this one because at this point, solving equations should for the most part be old hat to you guys. I'm going to leave you to your in-class assignments. If you have any questions about anything, by all means, please ask.